Hello, everybody. Today we're going to talk about topic 1.12, and it's going to be continuity over an interval rather than continuity at just one specific point. Ultimately, the definition is the same, and in order to be continuous over an interval, every point in that interval needs to be to satisfy the definition. It must exist, the limit must exist, and then the output has to equal the value of the limit, right? So it's the same criteria as continuity at a point. We just are going to look at a series of points rather than just one specifically. So if you take a look at example 1 here, we're going to look at the graph, and we need to, is it continuous at 2, right? And using our definition of continuity, we know that it is not continuous because there's a jump discontinuity. So I can say no. We do need to justify, right? Since the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x, the limit as x approaches 2 of f of x does not exist. Okay? Since the limit doesn't exist, we know that it can't be continuous. All right, so now the next question, is it continuous over the interval negative infinity to 2, inclusive on the 2? All right, now from negative infinity to 2, all right, we're looking at this, and you can see there's no breaks in my graph. There's nothing, going on here. Now the only piece of interest is at 2, but we defined in the last video, if you have an endpoint, it just needs to be the limit as I approach it from the left, right? If I'm talking about the right endpoint, the limit as I approach it from the left is equal to the output. So I'm going to say here, yes. And why is because for every x within, that's what this little symbol, every x within negative infinity to 2, we know f of x is going to equal the limit, actually I'm going to say a, as x approaches a of f of x. We know that this is going to be true. I'm going to use an a here instead of an x. For every a that's within negative infinity to 2, we know f of a is going to be equal to the limit as x approaches a of that function. So every point satisfies the definition of continuity. Okay. I should also be proper here. A is a real number within negative infinity to 2, right? So I'm defining what A is. If f of x is it continuous on all real numbers? And if I go from negative infinity to positive infinity, that includes 2. And I'm going to say no, because, and I'm going to say here that x equals 2 is a non-removable discontinuity, and that's within the interval negative infinity to infinity. And you can even go a step further, and you could say the limit as x approaches 2 of f of x does not exist. So I'm actually proving why it's a discontinuity, right? And because that point is within that interval, we know that it is going to, that interval is not continuous. Let's take a look at example 2. Is g of x, so we're going to call this g of x here, is g of x, excuse me, continuous at 1? The answer here is no. Why? The limit as x approaches 1 of f of x does not exist, right? Therefore, you can't have continuity. Is it continuous over all real numbers? Well, no. Why? It's the same reasoning. 1 is part of the real numbers. In order to be continuous over all real numbers, it has to satisfy the definition for all real numbers. So my answer for part B is going to be the same as my answer for part A. I'm going to say 1 is a real number, and then I can prove that it's not continuous at 1. Okay. Last but not least, this one's a little tricky for my students. Is g of x continuous over its domain? So ultimately, the domain of this function is negative infinity to 1, 1 to infinity. Now, 1 is not included in the domain. So my question is it continuous from negative infinity to 1, not inclusive on 1? Yeah, there's no breaks in my graph and in the left-hand side. Is it continuous from 1 to infinity? Yeah, it's there's no breaks in my graph from 1 to infinity. So therefore, this is continuous over the domain. And the reason being is because the domain is not including the asymptote. That's not a part of the function. There's no output there. So I'm going to say yes for every a within negative infinity to 1 union 1 to infinity. The limit as x approaches a of f of x is equal to f of a. And then, of course, define a is a real number within negative infinity to 1 union 1 to infinity, right? So for every value within that interval, we know that that definition of continuity is true. Okay. Let's take a look at these two graphs. So determine the intervals of continuity for the graphs, right? I want to know over what intervals is this graph continuous. Now, my graphs don't have it on here, but I do want you to make the assumption that there are arrows on the end of this, so my graphs will keep going. All right. So this first piece, you can see that I have discontinuity. So I'm going to start at x equals, we know there's a discontinuity at -4. We know there's a discontinuity at 2, and there's a discontinuity at +4. So we have 2 jumps and a hole. Okay. So I know that I'm going to go from negative infinity to -4, from -4 to 2, and then from 2 to 4, and then from 4 to infinity. So these are the intervals of which it's continuous. Now, I did not put -4 on there because we know there's a jump discontinuity at -4. I did not put 2 on there because there is a jump discontinuity at 2. I just want to know over what intervals is the function continuous. So everywhere where there's not a discontinuity. All right, same idea for the next one. There's some arrows here that are missing. But if I write for this, I'm going to say, okay, I have discontinuities at x equals -8, -2, 6, and I think those are the only 3. So my intervals of continuity are negative infinity to -8, -8 to -2, -2 to 6, 6 to infinity. Okay? And that's how I would write the intervals of continuity from a graph. Now, we're going to do the same thing. We're going to do the intervals of continuity from a function. But something I want you to understand. One, we need to know our basic functions, our function families, right? We need to know some of their characteristics, to do this appropriately. But I also want you to see some of these properties. If I know f of x is continuous and you multiply it by a constant, it's still going to be continuous. That's the first property, right? If you multiply it, if I know x squared is continuous, if I do a 2x squared, it's still continuous, right? So constants don't change anything. If you have a sum or difference of functions, okay, we're going to take a look at them individually. If they're continuous, if f is continuous and g is continuous, then I know when I add them together, that resulting function will still be continuous. Same thing with product. This should not be a multiply. This should be a times here. Same thing with a product. If I know that they're individually continuous at a point, when I multiply them, they're still going to be continuous at a point. Now, quotient is a little different. Quotient, if they're both continuous at a point, then the quotient is still continuous at a point. However, we might get an added discontinuity when the denominator is 0. So we always have to take a closer look at that denominator to know whether or not they're 0. So let's look at these functions. Let's try to identify where they're continuous. So 3 is just a constant. This is continuous over negative infinity to positive infinity. The radical, if you know anything about radical functions, oh, sorry about that, guys. Anything about radical functions, that's continuous from 0 to infinity. So we're going to take a look at these two intervals, and we're going to use the most restrictive, right? So this is going to be the most restrictive. Both pieces of this function are continuous over this interval. I can't go less than 0 because then the radical is no longer defined, okay? For part B, we're going to do the same idea. All right, the first function is continuous everywhere except for 1, right? Because I have x plus 1, x minus 1, all over x minus 1. This reduces, so I have a removable at 1, and I have no non-removables, right? And if you take a look, the limit as x approaches 1, excuse me here. So the limit as x approaches 1 of f of x, if you go from the left or from the right, if I plug in, that whole is going to be at 1 plus 1, in this case 2. And what I'm going to do is I'm going to fill in that whole. So believe it or not, if you graph this, the first piece of that piecewise function looks like this. And then the second piece of the piecewise function is just filling in that dot. So ultimately, where is this function continuous? Well, it's continuous over all real numbers. How do I know that? Well, the only discontinuity in the first piece of the piecewise was a whole or removable, but the second piece of the piecewise was a point that fills in that removable. So does the limit equal the output? Yeah. So every point from negative infinity to infinity will satisfy the definition of continuity. All right. Part C. So if we take a look at this, the top is continuous from negative infinity to infinity. The bottom is continuous from 0 to infinity. So I'm going to preliminary. Now I'm going to change this in a minute. So if I use the most restrictive out of these two pieces, I would start to say that it's continuous from 0 to infinity, right? However, if you were to plug 0 into the bottom here, you can't have a denominator of 0. So I need to alter this because I don't want to include where the denominator is 0. And in that case, it's my left endpoint. So I get this value. Okay. And then last but not least, let's take a look at this next one. It's very similar to part B. I have a line, 2x minus 4. So at negative 4, I'm going to go up 2 over 1. I'm going to go up 2 over 1. And I'm going to draw this. It does not exist at 3. However, at 3, I want to put a point of 1. So the question is this whole going to be at 1 or not? So if I take the limit as x approaches 3 of 2x minus 4, and you put 3 into that, you're going to get 2. That's different than f of 3, which is 1. So therefore, there's a discontinuity there. So my interval of continuity is going to be negative infinity to 3, union 3 to infinity. And that would be my answer. Okay, I hope this helped. Continuity over an interval, ultimately the same as the continuity at a point. We're just talking about a series of points instead of one individually. We're trying to identify, are there any points that fail the definition of continuity? Please let me know if you have any questions.